Hi, everybody. So today we'll continue on assembly programming. So if you remember in the last session, we ended up discussing about this important but very simple programming construct in assembly. As we discussed, we have like very similar construct that you can use in order to build, in order to write more complex uh, programs that can solve any sort of task that you can write in high-level languages such as C, C++, others. Um, Essentially, as I said, even though it's difficult somehow to write generic programs with arbitrary complex logic that we used to write in high-level languages, somehow relatively easier. Depending on the task, you can do the same essentially with assembly. And this is what it happens on the background when you write your program. Again, these are translated to machine code in order to get executed on the machine, right? So we can think about this correspondence between these languages. And these constructs, again, are useful to build this complexity based on the notion of abstraction that you have. Like abstractions always are helpful when we want to tackle complexity, right? These are the constructs that help us to think about writing programs, and it's very useful here as well, even though like the style slightly different somehow, but again, all of these constructs are pretty much useful and help us to write more interesting programs. Do you have any question about anything that we have discussed so far? Hopefully you started looking into your homework, right? So do you, I think you can, if you have any question about your homework, let me know. You have access. I mean, I try to provide enough description for this homework so you can understand what is the problem you want to solve and how you need to approach it. So that's going to be useful when to build up the intuition of approaching a problem, how to test it. So it somehow covers both problem solving and also like testing a program that you write using some test cases, essentially, right? In other languages, I'm sure you have seen test cases in terms of assertion, right? So when you use assertion in other, like for example, Python, and use some like example that you know that these are the answer should be a, like pre and post condition of a function. Essentially what we have in the routine that tests your program is pretty much the same what is happening, but now in assembly program. So hopefully you make these correspondences between these two. These are helpful to build the intuition, right? Again, learning matters when you try to solve it, try to build as much as intuition as possible in order to write better programs later on. Okay, let's start. We discussed about this programming construct. So let's briefly going through them. Again, the goal is to replace unit of work with some programming construct. So we have sequential, conditional, and iterative construct. And today we will have some examples of all of these. And if we get time, hopefully we write again one more program somehow to do it together again with a new construct that might be useful for you to know. For sequential, this is like when you want to basically break a task to multiple parts. And the intuition here is that you know how to solve easily these parts easier, and you know that the dependencies between these parts are sequential. So this sequential decomposition somehow is helpful and very simple, right? To break down into multiple steps and have them sequentially, solve them separately and put them sequentially to solve the task. And this is the way you know that the program is executed. And essentially, you know, again, repeating this, one of the fundamental characteristic of von Neumann model was the sequential execution, right? So one of the two fundamental key ideas was this sequential execution. Also, you see it in here as well. Conditional construct are basically useful. One of the important construct to have in your program that enable you to change the flow of sequential execution, right? To jump to some other part of the memory space where these different subtasks existed. So these subtasks could be located like different part of the memory. So with this condition, you could point, or you could like move to different part of the memory space, which would otherwise with this construct, without this construct, you could not, because again, like back to the one of these fundamental of von Neumann models, sequential execution. Without this condition, you would stuck. So you have this, you test this condition. If this is true, you execute one. If not, the other one. Very easy. One of these tasks could be also like do nothing, right? So for example, if a condition happens, do something, right? And then continue the rest, right? You will see one example, but you get what I mean. So not necessarily each test condition should have if part and else part, right? It could be only if part. Or it could be also somehow switch case, when instead of two subtasks, you might have multiple subtasks. And iterative are also useful, especially for calculation. You'll see some example today as well, where you test the condition and you do the subtask sequentially, right? So, for example, when in LC3, there is no notion of multiplication. So this having an iterative loop, iterative construct allow you to do multiplication using other instruction that you have. do the task, right? So like you have two numbers, you want to multiply them together, right? There's no multiplication construct how to do that. Like you will see, right? So you add like one number, the number of times of the other number, right? This is the way how we do a multiplication of two, for example, integers, right? So you do this, and you have like while, it could be do while loop, right? Or it could be a for loop. These are essentially, and you know that you can transform them, each of them, like into the other format, but you have these three flavors of loops. Right. For example, here we want to have a program that counts the number of occurrences of a character in a text file, and it uses all of these constructs. As a first example that you will see how we can use these constructs in order to do this task. And the task again, like, is count the number of occurrences of a character in a text file. Okay. And okay, so few detail like MIPS that we learned how to interact with input-output. You remember, through syscall, and also communicating a specific syscall utility through V0, right? Here in LC3, we also have similar, right? It's called trap instruction, where we somehow communicate with the input-output, and file finishes with the, in this case, end of text character. So this is a special character that we know. This basically is part of the specification of the program again. And in this example, UT is equal to 4, and the result should be again communicated to the output, written in a monitor, which is, again, we use trap instruction, right? So, and this is like the overall flow chart of the program, right? So again, you remember, like, we have a register where we should use in order to do the task. So obviously we need a counter. We use one of those registers as a counter. In this case, like R2, we initialize it to 0. And then we have a pointer. We initialize it to, we use R3 in order to essentially read the first character, or the characters in the file, right? And then the input character comes from the keyboard. Yes, Ralph.
So I'm just a little confused, because, like, I don't know, like, are we reading a file? Because it says input character from keyboard there, but like, that's different from, like, if we were reading a file and counting the occurrences of a character rather than, like, getting it from the input stream, right?
We read a file. The input is provided by the user, right? So for example, I have a file. I want to count the number of A in the file. This A comes from the user, and that's like how we read it through keyboard, right? But we read the file is in the memory, right? The file is already in the memory, but the character each time varies, and this will be provided by the user. Does it answer your question?
Yeah, I just wanted, I didn't know which one we were doing. Like, I just want to make, yeah.
Yeah, so basically the character is provided by the user and the file essentially is already in the memory. And we want to count like the number of occurrences of the character provided by the user right at the beginning. So we basically read the input character from the keyboard right here, trap x23, right? And then we get the character from the file, right? We read the first character. Again, this was pointing to the first memory address where the file is located in the memory, right? So we read the content of the memory and put the content in R1, okay? Here we check whether we have reached end of file, basically checking whether the character that we read is equal to end of EOT end of text or not. If that this is EOT character, then we basically are done. We need to put the result basically into a format which is represented, which can be represented into the output. So basically this is a simple transformation that we need to do, like adding a particular number to R2. R2, remember, R2 basically keeping the track of the occurrences. But like every time we want to print the content into output, like we need to like change the format to, for example, like ASCII format, right? We cannot send out the number itself, right? Here again, like this is the convention by LC3, but think about this as a somehow simple fixed transformation, right? And then we call this trap x21 for sending out the output, and then we again we send a stop signal, right? So again, this is another signal saying, hey, we are done. If it is not end of file, what happens is that we need to check. We need to check whether the character that we have just read from the file matches the one was provided by the user just at the beginning, right? So we match R1 with R0, whether these are equal or not. If not, basically, we need to move on to the next character. If yes, we need to increment R2, right? So R2 again was initialized to 0 at the beginning. So we increment by 1, and then we execute this logic here to move on to the next memory address, right? So we increment R3 and then we retrieve the next memory address, we put it to R1, and then we do the same, right? So it's very simple. Again, like here, you see how this construct that we discussed is used here, right? So let's discuss them right here. Like you see bunch of sequential steps, right? So you have used sequential construct here, right? We have if condition construct that we have used, and essentially this if condition with this jump that we have, we created a while loop, right? Essentially, this is correspondence of a while loop. So while this condition do this, right? So this is a while loop where inside it we somehow have a if condition construct, right? So we have sequential, we have a loop here, we have an if construct, and then we have some sequential steps here. So you see that like we reused all of these constructs that we have discussed for these simple programs. Unless your program is very simple, you definitely need all of these constructs in order to do your task. Again, unless it's very simple and you only like need sequential, right? Sometimes really you only need sequential. You don't need even a loop, but it really depends. Most interesting program, you need all of these program constructs. Do you have any question about this? Hopefully this is clear. But again, these very simple stuff are important to think about it. Maybe it's simple, doesn't matter, but it's important. It helps us to solve more complex tasks. Are there questions here? Can we email you if you have a question in the future? Yeah, why not? But again, like, what we prefer, right? We prefer if you have question, send it out to Piazza. So hopefully others can answer, and that's better, right? Yeah, you will see some of these examples, definitely. Yeah, absolutely. You can ask a question if you have about the homework on Piazza, and this is also definitely what I would encourage you. I mean, like, if you solve the problem, don't post the solution there. This is not allowed, but like you can, if like you have a specific question, you can definitely ask it on Piazza, especially if these questions are helpful, the way how others also thinking about the homework assignments and stuff, right? If you, again, like stuck somewhere, it's definitely useful to ask and somehow find a way to progress, right? This is again about learning, right? It is absolutely fine if you stuck somewhere to ask for help, right? But again, like, you should make sure that throughout this course you learn, and next time you do much better. Okay. So this is the way how you should think about it. But again, like if you have question, if you stuck somewhere, it is absolutely okay, and I highly encourage you again, like use this opportunity in the class specifically to ask your question here. Don't be shy. Again, like I'm not scary. Ask your question here. This is what I prefer. But also like post your question on Piazza. Hopefully other classmates can help answer what me and also your TA will look into these questions, and whenever necessary, we will provide answers. Okay. Yeah, so we discussed about this, right? Yeah. Yeah, trap again is a operating system call, right? Where has a specific format, machine format, right? Similar to other instruction in LC3. So you have some opcode 4 bits, and then you have some 8 bits to communicate this specific signal you want to send. And the opcode is 11141, basically. And these 8 bits is called service call. Like again, syscall, where in MIPS we use, again, here like this number for input a character from a keyboard, 21 again in hex for output a character to a monitor. So again, think about it like input output in the machine, communicating with the operating system to carry out this for you. And like OX 25 for halting the program, exiting the program. And this is like how it looks like in memory, right, when it is encoded. So this is, let's go quickly like to this, but this is essentially what after you encode it, translation happen to machine code, right? So here the how initialization happen again. Typically we use like and for initializing and with 0. So it's a simple way of initializing a variable in LC3, right? And if you remember do you remember how we initialize in MIPS? Anyone remember how we initialize a variable in MIPS? Don't be shy. It's very simple. So you want to initialize a register in to 0, right? We have done it together last time, right? No, do you have something?
Yeah, wouldn't you just load the register with load immediate or load address and then set the value of that register to 0? Or I have something wrong there, I think.
Yeah, we want to set the value of a particular register to 0, right? So essentially what I'm asking, setting a particular variable to 0, but so there is no loading happening, but we want to set the value of a variable, value of a register into 0, because essentially these like, so before even like how to do it, how to set it to 0, why we want to set it to 0? Why?
In this case or in general?
In general, in this case or in MIPS, or in general, right?
Um,
High-level languages, why we want to set a variable to 0?
If you want to use it for like iteration, or if you want to use it for keeping track of a value, you'd want to start it at 0. This is just one example. Or if you need to reset something.
That's right. But like, for example, like, let's say we want to use R2 or like, let's say T0 in MIPS as a counter, right? So you're right. So we want to set it to 0 because like we want to do something with it. But why we cannot right away start using it like T0? Like why we cannot start right away, like at the beginning of the program, why we cannot just use it without setting to 0?
Because it's null until you assign it to something or
Not
initialize it.
I mean, it's not a high-level language. That's a good thing to discuss, right? It's not a high-level language. Like it's C, yes, you want to initialize it because like you need to initialize it. Like you cannot use it before, right? Because it's null, right? It really depends on the semantic of the program, right? But essentially, most of the programming languages, this is the case. But like in assembly, like these R1 to R0 to R7 in LC3 are there. Like all of the registers in MIPS are also there. You don't need to like initialize it because they are null, right? They're there, right? You can start using them right away. Why we want to initialize them? These are important questions that I'm asking.
I mean, you can't iterate on it if it doesn't have some numeric value, or use it and really. And I mean, like, there's no use for it if it's null, is what I was trying to say before. Like, you can't do anything with it. I guess, I mean, just in kind of in general. Like if you just declare it, like, I mean, well, I mean, I don't really know if you could do that in assembly, but
that's a good point. That's a very good point, right? So again, like in like assembly, there is no need for declaration because again, and that's important, right? Because they're there, right? You don't need to declare a register, right? You can like there is no need for declaration. They are there, right? You can use them whenever you want without any sort of declaration, right? So they are like a special memory, right? Very fast, where you can like use them anytime, at any time. You don't really need for any sort of declaration. These are like different from like variables in high-level language that you need to declare them. Like when you declare a variable in high-level language, like you declare a variable, but really you need to like initialize them before using them because like they are not when you declare they are not assigned to a particular part of the memory yet, right? When you initialize them, then like this assignment happens. But here in assembly, like think about it that they are pre-allocated for you to like use them anytime. But again, like why we want to initialize them? This is definitely not a declaration, but these are very good point. Good point. You don't need to create a register, but if you don't define the register to an initial value, won't whatever info was already stored there affect your initial code? Brilliant, right? That's the answer I wanted to hear, right? They're there. You can use them anytime. But what is the guarantee that like you don't have a random number there, somebody, some other like part of the code haven't left anything there, right? You want to ensure that it is initialized to 0 because you want to rely on the value that there's no guarantee. Essentially, there's no guarantee that whenever you want to use a register, 0 is there, right? So it's not initialized to 0 at the beginning, right? So every time you want to use, you want to make it clean. You want to make it yourself, right? But again, like there are some, we discuss it, like for example, when you want to use a register, when you call a method, when you want to use a register there, you also should make sure that you do not overwrite a register that will need it in your like program, right? If you overwrite there, then you mess around with the logic that is happening in your main or other part of the program, right? So these are some details that you need to know and you need to take care of explicitly, right? So some of these are by default will be taken care of, right? So for example, when you call a method in high-level language, you don't care like whatever variable you change there, right? Because like these abstractions are in a way that like you have different memory addresses there, and like you cannot mess around. You can if you want, but like you don't need to be worried about the variables that you use in your main program, right? But in assembly, like these are like shared registers between all part of your program. So if you call a method and if you like change a register content where you don't have to and it is needed in your main procedure, then you violated the semantic of the code. So things could go wrong. Again, like, so here we definitely need to initialize a counter because we need to make sure it is 0 at the beginning. This is what we rely on, right? The semantic of your code rely on this, okay? So you initialize the address, again, R3 pointing to the first memory address. And here we assume that this is the first memory address, right? 3012. Okay, and so this is, we use LD, and then we need to read the input character, put it to R0, right? And then here we put the MR3, the first character from the file, put it to R1, and then R4 here basically we check here we basically that's a good thing, and you will see why we need to like deduce -4 from R4. Basically, we deduct end of file from R1 because we want to check next time. We want to use this branch BR0 branch if 0, right? in order to check end of the file, right? So basically here, when we reach this condition, after we this instruction has been executed, if R4 becomes 0, when R4 becomes 0, when basically R1 is end of file, right? And that's why we do this operation. We deduce 4 out of R1 to check whether this becomes 0. If this becomes 0, then you jump out of the loop because you're done, right? This is where the rest of the where the rest of the program happens, right? So essentially you do the transformation and you send it to the monitor. Basically, this is where you're done. But if not, what's happening is that you here you use not in order to transform R1, and you will see why. And then you add +1 here, right? And then you add it to R0, right? So basically, this is a logic that you need to do, because here again you want to use one of these branches, right? So again, going back to the flow chart here, what you need to do, you need to in FC3 again. You have this flexibility of having different branch condition through this BR NZP, right? Like here you see that we use branch 0 because it was very easy to check whether we reach end of file. So if R1 is end of file, we know that EOD code is 4. Basically, we could check it easily with BR0 and do the task. Here we want to check the equality between two character that is provided by the user putting into R0, and the character that is provided by that has been read from the file, right? So R1 contains the first or basically a character in the file that has been just read, and we want to basically compare it with the user provided character, right? Can anyone make sense out of this instruction? Why this instruction happens? What they do? What is the logic behind this, right? Why we use not here, why we add 1 here, and why we add them together? What's going on here? Why we did all of these like nonsense stuff here?
Is it to convert with 2's complement?
Okay. So can you elaborate on that?
It just looked like, so we invert it and then add 1, which is similar, which is the operation that we do when we want to find the 2's complement for a binary number. And then after that, it just adds that to your register at 0, or adds your current position to it. So it converts it to an ASCII code for our character.
Here, you mean?
There, and then with the next part down, R0 is the current register for the beginning of the file. No, I got that wrong. My bad.
You are somehow partially correct. So, but make the connection with this instruction as well. Like, why all of these, like having these tools complement here, why we add these together, and then why we have this instruction here. I again reminded you BRNP is branch if what was N?
Negative?
Negative and positive, right? So what it means?
You're going to branch as long as it's not a 0 value.
Exactly. So if the value is 0, basically you don't branch. But if the value is either negative or positive, you branch, right? So can you now make a connection with the semantic of the code here?
That part of the code just looks for our end of file character, that sentinel character. Then
No. We check the end of file here. So if it was end of file, we are here, right? So we are done. But here, if it was end of file, we were not getting to here. But here we are like doing some stuff. As you said, like we take a 2's complement here, but why? Why? It's not difficult. It's important. That's why I'm waiting, because I want you to like understand what is the logic behind it. Yeah, go ahead.
Well, you'd be doing the binary subtraction. That's the only way you can do binary subtraction is through 2's complement. You can't like you have to add the 2's complement to get to subtract. And if you compare those, so yeah, and then so you make a negative, and then if the result of subtracting those 2 characters is negative, then you know that they're the same character. Or sorry, 0. If it's 0, the same character.
Brilliant. That's absolutely okay. Perfect. So basically, what's happening? There is no like checking whether these 2 registers are equal, right? In LC3, like what we want to do, we want to subtract them and see whether the result is 0 or not. If the result is 0, means that these 2 had the same value. So if you subtract them, the result is 0. But if they are not equal, it could be either positive or negative, like which one was like greater, right? So it could be either positive or negative if they are not equal. And that's what's happening here. So we subtract them, and then we use branch NP. So essentially, if they are equal, this branch won't happen. So you move on to the next step. But if they are not equal, you basically Is this true? Yes, and yeah, here I thought probably we increment the R2, but here we increment R3, right? So we want to go to the next memory instruction, right? Basically, these are not equal. We increment R3, otherwise we increment the counter, right? Because one occurrence happened. And then we move on to the next character from the file. And here, we use what is brNZP? Remember? brNZP. You're muted now.
That branches regardless because it branches on a 0, negative, or a positive. So you're using that to reset back up to the beginning of your loop.
Excellent. So this unconditional branch, no matter what it branches, why we want to go there 3004, where it is here? Why we want to go here?
That's the beginning of your loop. You want to go back up so you can go to you can iterate through the next character in the file.
To basically simulate the while loop, because at the end we want to, no matter what, we want to go at the beginning of the while loop, right? This is what happens. Excellent. And then the rest, we know what's happened. So this is the way how you can implement in LCT. Yeah, Russ.
Just quickly, why like at 3004, wouldn't you like? Why do we have to do two's complement for the those instructions, but not for that subtraction? Like, why is that just? Why can we just directly subtract there as opposed to doing two's complement there as well with the 3 instructions that we used below?
You mean why we didn't use two's complement here?
Yeah, like because we used to direct subtraction, but like we had to go through the two's complement below to subtract.
Oh, because here, like, we know end of file. So basically here what is happening, we use add instruction, but we know the value of end of file here, right? So, and essentially two's complement happening here, right? So it's already encoded. So we have two's complement of 4 in here, right? So this is
Gotcha.
This is what has already happened, right?
Okay, gotcha. Thank you.
Sure. So basically, and here, like, we know like the value of this. So yeah, good question. Very good. And then like the rest, I guess this is that should be obvious for you now. So so let's recap again, right? So what beyond the instruction that we have here, like, what was the takeaway? Again, like, these are important. First, there are some like simple stuff that like they are taken away, like in high level languages. We don't need it like to like do some crazy stuff for some simple instruction. Like for example, for checking equality, we needed to like use multiple instruction to check that for us, like in high level languages. And even in some like other ISAs, we have check for equality. But again, like in some ISAs, you don't have even instruction for some basic stuff. And these are like, again, all computer architecture is about trade-off, right? You know that, like, why, again, like going back to this important question, why, for example, designer of LC3 decided not to have equal condition or some other like basic stuff? What was the reason? Like, for example, even like multiplication, right? necessarily we don't have any instruction for multiplication, right? But we have like instruction for adding. Why is the reason, like why these are not provided by default?
Is maybe it's I remember you saying the purpose of like assembly is to like, we could use it to optimize our code, and if like you have access to the bare bones of every operation rather than being able to just always be at a higher level, like you're actually at a level where you can control like the operations, so it could affect efficiency. Like you don't always need to do things the high level way, and this allows you to fine tune it. Kind of is kind of what I was thinking.
Somehow, but like, couldn't the designer of LC3? I mean, like, yes, I don't expect like matrix multiplication. Why not like two numbers integer multiplication, right? Like other like x86, for example, has this like even more complex instructions that can do like more complex stuff. Why in LC3 or like some other stuff in MIPS we don't have these? We discussed this before. Can anyone elaborate? Simple. Again, like I'm asking because these are like, you want to get back to the stuff that we have discussed to learn why, because these are important.
It's easier to understand.
It's easier to understand, not really. So like if you had like simple stuff like equalities, would have been easier to understand the code, right? Definitely, rather than these 3 steps of like doing some stuff in order to implement whether these two characters are equal or not.
Does it have to do with having a limited number of opcodes?
Yes, yes. Yes, but do you want to a little bit generalize on that? That's a correct answer.
Okay, so you only have 2 to the 4 different possible opcodes, so you don't want to waste one of your opcodes for an operation that can easily be done with any of the others that you already have. You might need 1 or 2 more instructions.
Right. Why, for example, they didn't allocate more opcodes? Like instead of 4 bits, like why not 6 bits?
That the more bits you use for opcodes, the less bits you have for things such as your storage in your registers or for your branch statements.
Right.
And that's, and LC3 is 16-bit as opposed to MIPS, which is 32-bit.
Right. So why not like using like more bits in total for memory? Like instead of 16, like why not 32?
It keeps your programs a lot smaller when you're running them. So if you need to work on a machine that has less memory.
Yeah, all of these answers are perfect. They're all correct. And essentially it gets back to the complexity, right? So if you have like more number of bits to allocate for opcode, like you have less for other stuff, and like you cannot fit everything together. Like you have like 16 bits to encode everything that you need. You could use in total like 32-bit, but like, yeah, the cost would go up. Even if you could encode more instruction, you need some hardware to implement these instructions, right? So you needed to have like more complex implementation of all of these instructions at the hardware level, right? Because at the end of the day, like these stuff are implemented in your macro architecture with these like logic gates, right? So you needed more logic gates. All of this will be translated into like more stuff in the macro architecture and more stuff down like more number of transistors. If you have more number of need more number of transistors, like obviously you need to pay more, right? And the cost of your computer become higher, more expensive, right? This is again back to the trade-off, and that was actually before like RISC ISA, like MIPS's RISC, right, reduced instruction, right. It was like previous generation was like having a CISC type where at the ISA level, we have more complex instructions, right? But the key intuition behind RISC type architecture was that you could do the same thing even much more efficiently if you have reduced instructions in terms of like not only cost, but also in terms of like energy, all of this, right? You could do the same, like Hennessy and Patterson showed that essentially you could build a computer with basically less number of instructions, more simple instruction, doing the same stuff, even with better efficiency in this term, rather comparing with the CISC generation. And that was the, somehow this revolution in RISC type of architectures that happened over the past decades, right? So again, these are like trade-offs. These are basically affect both performance, cost, but also you see that like when you want to write program, you need to like write more instruction. You need to use other instruction in order to implement the instruction that you don't have, right? For like comparing to like registers, whether these two are equal or not, right? But you could do it through like this simple way of like two's complement and like adding them together, basically essentially negating these two, subtracting these two, and checking whether these are zero or not, the result. Yeah, so basically this trade-off is happening, but your program, your assembly program become more complex as a result. If you had these instructions, your program could be compact, right? You could ask this, like your program could be compact, but like what's happening here is that you could write, and that was the key intuition, you could write a nice compiler, like you could make your compiler more complex to do this translation, because at the end of the day, like we don't want to write these assembly programs, machine code ourselves. This will be done by compiler, right? If you write more complex compiler, you could fill this semantic gap. So you could assume on simple instruction set. Obviously, your assembly program becomes like more complex as a result, but you could fill this gap by a software that does this translation, which is called compiler, you know. But on the other hand, like the cost of your hardware becomes a lot cheaper, right? That's the kind of trade-off space we are talking about. We discussed about that, but now I'm 100% sure that you have better intuition, when we have examples, right? So at the time we discussed this, probably like you couldn't see why, but now clearly you see why, right? And this is again important. We wanted to mention about this. Okay, we have a few minutes. Maybe let's also finish this, and then next week we have some also. Yeah, today we did not get time to do this live programming, but next week we will do again to have fun. Yeah. So I think we discussed about all of this. Yeah, here this is a while loop happening. This is discussed. Yeah, and here is if condition. So basically, we have these all of these construct, and essentially, like what we plan to do, and we somehow did it together. But now we want to discuss more explicitly, right? This is, you see what's happening, right? We did live programming and also debugging for simple examples. Now the plan is to discuss more explicitly how we do this debugging in practice, and also we will have some specific examples like next week when we discuss this debugging in detail. But at the same time, we will do one debugging in more complex program, relatively more complex program, to somehow see again, in order to help you to build up this intuition and how important it is. Because I'm sure, like, when you start writing your solving the homework, you will need debugging skills in order to solve the task, in order to find any potential bugs if exist in your program, and how you can do it more efficiently and utilize the stuff that, like, you have in a SPIM, right? For example, breakpoint stuff, and reading from registers, memory, in order to find any potential bug in your program. Is there any question? Yeah, I will stay here for a few minutes if anyone has question, please. But yeah, let's just stop here, and we'll continue next week. Have a great weekend, and stay safe. See you next week, and yeah.
Thank you.
Sure.